In section 6.3, this is the beginning of module 2. We start by looking at graphs of sine and cosine functions. The rest of this chapter we'll be working a lot with graphs of really all the trig functions that we've talked about. So we start off with the definition of a periodic function. A periodic function is a function f such that f of x is equal to f of x plus n times p. For every real number x in the domain of f, every integer n, and some positive real number p. The possible positive value of p is the period of the function. Okay, so what's happening with a periodic function is you're going to have an interval where you have something happening on your graph. And then once you get beyond that interval, it's going to continue, it's going to repeat, do the same thing over and over again. Alright, so we're going to start with the graph of sine of x. Alright, so how do we go about graphing a sine function? Well, before we can set up a table of values, we want to look at what happens with a unit circle. So let's just look at the quadrantal angles. In other words, the angles where the terminal side actually sits on the x or the y axis. Okay, from the unit circle, so let's say if I wanted to evaluate sine of 0, sine of pi over 2, sine of pi, sine of 3 pi over 2, etc. Let's see what kind of values we would get. So I'm going to do, if I do sine of 0, what is sine of 0? Well, from the unit circle, I know that I've got ordered pair here at 1, 0. Okay, so sine of 0 would be the y value 0. For sine of pi over 2, now I'm over here, so I go to angle pi over 2, and on the unit circle, my ordered pair is going to be 0, 1. So sine of pi over 2 is 1. Okay, this should say sine of pi. Okay, sorry about the little squiggle there. Sine of pi, so I get that by coming all the way over here to angle pi, and here my ordered pair is negative 1, 0. So sine of pi is negative 1. Sine of 3 pi over 2, so that's going to be the 270 degree angle down here. Sine here is going to be, that's going to be ordered pair 0, negative 1. So sine would be negative 1. Oh, I'm sorry, I goofed up here. Sine of pi is the y-coordinate from back here. So my y-coordinate is 0. Sine of pi would be 0. What's sine of 2 pi? Oh, well, 2 pi is the full rotation and brings us all the way back to our starting point. So angle 2 pi is the same as angle 0. And sine is the y-coordinate, so it's also 0. So this gives us ordered pairs that we can work with to graph our sine function. The values that we put inside the sine function in each step are going to be our x's, and the answers that we're getting over here are going to be our y values. So if I take these, if I create a list of ordered pairs using these values, these for x and these for y, I get the table on the next page. Okay, so as I saw, when x was 0, y was also 0. When x was pi over 2, we calculated sine of pi over 2 to be 1. Alright, sine of pi was equal to 0. Sine of 3 pi over 2 was negative 1. Sine of 2 pi was 0. So let's plot these ordered pairs. Now, probably one of the things, maybe the more challenging aspects of this material, may be having to get used to using radian measure on your x-axis. Most people are not used to putting pi over 2, 3 pi over 2, etc. on their x-axis, but because we're working in radians, our angles are always going to be measured in using radians, which is going to use pi. So we're going to have to get used to using these x values involving pi. Okay, so let's find these ordered pairs. We've got ordered pair 0, 0. Then we've got when x is pi over 2, y is 1. When x is pi, y is 0 again. When x is 3 pi over 2, y is negative 1, so it's down here. And when x is 2 pi, y is 0, so that puts us there. So we get our sine function by connecting these dots with smooth curves. So we're going to go up like this, and then we're going to come back down. Just make sure it's in like a smooth curve shape and not straight lines. Like this. So that gives us the sine function from 0 to 2 pi. And as we know from the unit circle, if we continue beyond 2 pi, it's just going to go around and give us the same y values again. Okay, so this is the function, the graph of y equals sine x from 0 to 2 pi. Alright, so let's talk about the features of this graph. Y equals sine of x has the following characteristics. The domain is negative infinity to positive infinity. I did not indicate that on the graph, but this does continue forever from the left to the right. It goes this way forever, this way forever. The range goes from negative 1 to positive 1. And we've talked about the range of this before. Excuse me. The x-intercepts have x values of the form n times pi, where n is an integer. So our x-intercepts on the sine function are always going to be some multiple of pi. Our period is 2 pi. Now what is the period? Well, the period is a complete cycle of this function. So this function goes through one complete cycle at 2 pi. The function is odd. In other words, it's symmetric with respect to the origin. So as you go up, any point that you find up here, you can find a corresponding point by changing the sign on both the x and the y values. Alright, let's take a look at the graph of the cosine function. So again, we begin by evaluating cosine of the quadrantal angles. So cosine of 0 would be found on the unit circle here. And we know that order pair to be 1, 0. The x-coordinate is 1. Cosine pi over 2 would be 0. Cosine pi is negative 1. Cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is the same as cosine of 0, is also 1. And you can see how it begins to repeat after that. So we could fill in our table. So when x equals 0, y equals 1. You have to excuse me, I've got my 3-year-old in here helping me today. Cosine of pi over 2 would be 0. Cosine of pi would be negative 1. Okay. All right, here you go. Cosine of 3 pi over 2 is 0, and cosine of 2 pi is 1. All right, and then we can plot these points on our graph. So 0, 1, then pi over 2 for x, 0 for y, then pi and negative 1. We have another x-intercept at 3 pi over 2, and then we have a point in 2 pi, 1. Okay, and just like before, we connect these dots using a smooth curve. So we're going to get a graph that looks like this. Okay, this is a complete cycle of the cosine function. If we continued, it's just going to do the same thing over and over again in both directions. So it also has period 2 pi. From 0 to 2 pi is one complete cycle. And if you compare it to the sine function, if you go back and look at the previous graph that we did for sine, you'll see that it looks like a sine function that's just been shifted over pi over 2 to the right. Alright, so characteristics of the cosine function. Go on to page 4. Okay. It also has domain negative infinity to positive infinity, and its range goes from negative 1 to positive 1. The x-intercepts have x values of the form 2n plus 1 times pi over 2, where n is an integer. Okay, and that's similar to what we said for sine. It's just that now you have odd multiples of pi over 2, whereas before we might have had even multiples of pi over 2. Its period is 2 pi, so that means a complete cycle has length 2 pi. The function is even because it is symmetric with respect to the y-axis. So let's look at the picture again. Okay, remember symmetry with respect to the y-axis. You don't really see it in this picture because I only drew one cycle, but if I were to draw another cycle over here, it would follow this exact same pattern. So so if we included 2 periods from negative 2 pi to positive 2 pi, you would have symmetry with respect to the y-axis. Okay, and because it's got symmetry with respect to the y-axis, that makes it an even function. And even and odd functions are going to be important a little bit later for what we're doing. So let's look at an example. In example 1, we're asked to graph y equal 2 times sine x and compare the graph to y equal the sine of x, which we just did. So in order to graph this, we're going to go through and do what we did before for sine. So we did sine already. And then we're going to do another column where we just multiply our results by the 2 in the front. We want to see what happens. What does this 2 sitting in the front do to the original function? So our values for sine, when x equals 0, y equals 0. When x equals pi over 2, sine of pi over 2 was 1. Sine of pi was 0. Sine of 3 pi over 2 was negative 1, and sine of 2 pi was 0. Alright, what happens if I multiply all this by 2? Well, 2 times sine of x is still 0. 2 times 1 is 2. 2 times 0 is 0. 2 times negative 1 is negative 2. And 2 times 0 is 0. Okay, so what does this look like when we graph it? So these are going to be our x's, and these are going to be our y's. So we've completed our table for 2 times sine of x, and now we want to see how it compares with our original function. Okay, so when I go to plot my points, I'm going to be graphing, oops, I can't get it all together, but maybe I can. There we go. So I need to graph ordered pair 0, 0. Well, that was the same. That was on the original. Now I need to ordered pair pi over 2, comma 2. So pi over 2 on x, but I go up here to 2 for y. And then I need to ordered pair pi, comma 0. So I got another x-intercept of pi. I need an ordered pair 3 pi over 2 on x and negative 2 on y. So that's going to put me down here. And then I've got ordered pair 2 pi, 0, so another x-intercept. So what does it look like is happening to my graph? Let's get that over for you, okay? It looks like it's the same, but this is, you probably, you might recognize this as a vertical stretch. And a vertical stretch, if you recall from Math 171, a vertical stretch of a function always occurs if you multiply a number larger than 1 to the original function. So if you've got a 5, so you saw this with your parabolas, absolute value functions. The same rule applies with the trig functions. If you multiply the function by a number larger than 1, that gives you that vertical stretch that you saw in 171. Okay, that's exactly what's happening here. So we can connect these with a smooth curve like we did before. Okay, and that's what our graph looks like. Okay, now the dotted line is the original. This was the original sine function. Okay, and then you can see how it compares to our new one. Amplitude of a periodic function is half the distance between the maximum and the minimum values. Okay, so amplitude would be the distance from the x-axis to the peak, or you could also say it's the distance from the from the valley to the x-axis. So it's the absolute value of the difference between the x-axis to either the peak or to the valley. Okay, that amplitude will always come from this same coefficient that we multiplied the function by. Okay, so in 171 you might have said that you had a vertical stretch by a factor of 2. Okay, and in the sine and cosine functions, it's just going to also give us the amplitude, the distance from the x-axis to the peak or to the valley. Okay, so the graph of y equal a times sine of x, or y equal a times cosine of x, is a vertical stretch of the graph y equals sine of x or y equal cosine of x whenever a is greater than 1. And just like you saw in 171, if you multiply a function by a number that's smaller than 1 but still positive, so between 0 and 1, you're going to get a vertical shrink. It's going to get squished. So the graph of y equal a times sine of x or y equal a times cosine of x is a vertical shrink of the original graph if a is between 0 and 1. And then we just state again that the amplitude would be the absolute value of a. So a was the coefficient, the number that we multiplied the function by. The absolute value of that number gives you amplitude for sine and cosine functions. So if you understood graphing in 171, you are this shouldn't be too hard for you. So in the previous examples, we saw how multiplying a function by a number larger than 1 affects its graph, or how it would affect it if we multiplied by a number smaller than between 0 and 1. What happens if we multiply our x value by a number instead of our y? So in the functions y equals sine x and y equals cosine x, the coefficient on x affects the period. In other words, the period is how long it takes to complete a full cycle of your function. So in example 2, we're going to graph the equation y equals sine of 2x and compare with the original graph of sine x. So this time I'm putting in I'm making a little bit of a change to the values that I'm putting in for my x. I'll talk more about why I know to do that in a little bit. But for our purposes for now, we're going to use, what I've done is I took the values that we put in for x in the original sine function, but I've also put the x value in between each pair of values that we originally used. So originally we did 0 and pi over 2. This time we're also going to do pi over 4. So if I put in 0 for x, well, if I put in 0, I've still got sine of 2 times 0. That's still sine 0. And we know that sine of 0 is 0. If I put in pi over 4 for x, then I've got sine of 2 pi over 4, which is sine of pi over 2. And we know that sine of pi over 2 is equal to 1. If I put in pi over 2 for x, then I've got sine of 2 times pi over 2. And that's just sine of pi, and I know that sine of pi is 0. Put in 3 pi over 4, so you've got sine of 2 times 3 pi over 4. So that's going to be sine of, and that's going to be 3 pi over 2. Okay, sine of 3 pi over 2, we know from the unit circle to be -1. Alright, if I put in pi for x, that gives me sine of 2 pi. Sine of 2 pi is 0. If I put in 5 pi over 4, I've got sine of 2 times 5 pi over 4, which is sine of 5 pi over 2. Alright, so I'm getting sine of 5 pi over 2. Now what is sine of 5 pi over 2? Well, 5 pi over 2 would be, here's pi over 2. That would be pi, or 2, I'm sorry, you can't see it. So looking at the unit circle, alright, we're finding sine of 5 pi over 2. Alright, so this is sine of 0, this will be 5, excuse me. Starting here, this is 0 degrees, and then here we are at pi over 2. This is 2 pi over 2, 3 pi over 2, 4 pi over 2, and there's 5 pi over 2. That's the same, that's the reference, so the reference angle for sine of pi, the reference angle for the sine of 5 pi over 2 is the same thing as finding the sine of pi over 2. Alright, so what's the sine of pi over 2? That's 1. Okay. What about 7 pi over 4? So now we're going to do sine 2 times 7 pi over 4. That's going to be sine of 7 pi over 2. And then what's 7 pi over 2? What's the reference angle for 7 pi over 2? Well, look at the unit circle again. Here's pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. Here's 7 pi over 2. The reference angle for that is 3 pi over 2. So we need sine of 3 pi over 2, and we know that's negative 1. So I got that by doing sine of 3 pi over 2, because 3 pi over 2 was my reference angle, and that was negative 1. Okay. And let's see, I'm sorry, I goofed up. That was 7 pi over 4. That goes on this line here, and I accidentally skipped this line. So I need to go back and pick up 3 pi over 2. So sine of 3 pi over 2, so I'm running out of scratch paper here, so sine of 3 pi over 2 is what I need to do sine of 2 times 3 pi over 2. So that would be sine of 3 pi. And what is sine of 3 pi? Well, sine of 3 pi, let me draw a picture. Alright, well, here's pi, there's 2 pi, 3 pi is back over here at 1 pi. So you're finding sine, there's 3 pi right there. Sine of 3 pi would be negative 1. I'm sorry, that's not right. What's the sine? This is at negative 1 comma 0. Sine of 3 pi would be 0. Alright, and then finally 2 pi, we're going to do sine of 2 times 2 pi. That's going to be sine of 4 pi. Okay, but we know that the reference angle for this is just 0 degrees, because that's the starting point. I guess after you've gone around 2 times. So if you start over here, alright, that's 2 pi, go around again, you're at 4 pi, so you're back over here where you started from, and your y-coordinate now would be 0. So sine of 2 pi would, sine of 4 pi would be 0. Alright, now so here's our table that we filled in. If we plot those points, we'll get to see how that coefficient on x affected the original sine function. So let's see, we need to find order pair 0, 0 at the origin. We need order pair pi over 4, comma 1. That's going to put us here. Okay, so we've got order pair 0, 0 and ordered pair, this is pi over 4, 1 here. And then we've got pi over 2, 0. Three pi over 4 on x, that's going to be this one, and the negative 1 is there. Now we've got order pair pi, comma 0 is here. Oh, I'm sorry, this should be down here. And I don't have any white out. So these are the dots I've got. 0, 0, I've got pi over 4, 1, pi over 2, and then I've got this one down here, and I'm sorry about that one, just trying not to look at it. Okay, and then we've got pi 0. Now we need to graph 5 pi over 4, so pi is 4 pi over 4, the next tick mark is 5 pi over 4. So 5 pi over 4 and 1. Then 3 pi over 2 and 0. And then 7 pi over 4, that's one space before you get to 2 pi, and the negative 1 here. And then 2 pi, 0. Okay, so now we can connect our dots with smooth curves. Let's see what it's doing to our... Now, notice what happened. All right, what does that look like? That's one period of our sine function is complete by the time I get to pi. And then if I continue, I've got a second period. So what happened by multiplying x by 2 inside the sine function is that it shortened our period, and we were able to complete two full periods from 0 to 2 pi. Okay, so that's what our graph looked like. Okay, so let's talk about period. For b greater than 0, the graph of y equals sine of b times x has period 2 pi over b, so this is important, you'll need to remember this. And the graph of y equal cosine of bx also has period 2 pi over b. Okay, in example 3, we're asked to graph y equal cosine of 2/3 x over 1 period. So the first question we ask ourselves is, all right, so what is the period going to be? We need to know what the period is so that we can label our x-axis correctly. We need to know what values to put in for x. So we need to determine our period first. And from our rule up here, we know that the period is going to be 2 pi over b. And b is equal to 2/3. Okay? So to find our period, we need to do 2 pi over b, which is 2/3, and simplify this. So that's going to be 2 pi times 3/2, or 3 pi. So our period is going to be 3 pi. Alright, and once we know our period, let's take a moment to just think about amplitude. What is amplitude going to be here? Remember, we get that by looking at the coefficient in front of the function. And this one is just a 1 in the front, so our amplitude is going to be 1. So we're not going to have any type of vertical stretching or vertical shrinking going on in this problem. But I'm going to say my amplitude is 1. Okay, so that just means my max and min values will be at 1. Okay, now that we know our period, we need to divide it up into 4 equal intervals. So let's look at how to do that. So we're going to go from 0 to 3 pi. Alright, to get the halfway point, we just need half of 3 pi. Or in other words, you would add the starting point and the 3 pi for your period, and then divide by 2. So that's going to give us 3 pi over 2, because 3/2 is half of 3. And then you need to do the same here and here. So we need a midpoint there and a midpoint there. So we need half of 3 pi over 2. Well, that's going to be 3 pi over 4. And then to figure out this part, you've got 3 over 4. Okay, this will be 6 over 4. This will be 9 over 4, and then 3 is 12 over 4. So once we have our period determined, in order to know how to put values in for x, we have to divide it into 4 equal intervals. So we first did half of 3 pi to get the midpoint, and then we found the midpoint of 0 to 3 pi over 2 to get 3 pi over 4. And then you just have to kind of familiarize yourself with the way the fractions work. 3 over 4, or 3 pi over 4 here, and then that's going to be 6 pi over 4, that's 9 pi over 4, and that's 12 pi over 4. Okay, but once you've got that determined, now you know how to set up your table. And I'm running a little bit tight on space here, so I think I can get my table in here. So we're going to do x, and then we want to do y equal cosine of 2/3 x. So we'll do x equals 0, x equals 3 pi over 4, 3 pi over 2, 9 pi over 4, and 3 pi. Okay, so those are going to be our intervals, or our x values. Okay, so if we put 0 in for x, that's going to give me cosine of 0. Cosine of 0 is going to give me 1. If I put in 3 pi over 4 for my x, then I've got cosine of 2/3 times 3 pi over 4. So that's going to be cosine of pi over 2. And cosine pi over 2 is 0. Okay? Then we need cosine of 2/3 times, and we're putting in the 3 pi over 2 this time. That's going to give me cosine of pi. And cosine of pi is -1. Alright, now we put in we put in 9 pi over 4. So cosine of 2/3 times 9 pi over 4. That's going to be cosine of 3 pi over 2. Cosine of 3 pi over 2, that's just another quadrantal, that is 0. And then finally cosine of 3 pi, I'm sorry, not cosine of 3 pi. We put 3 pi in place of x, so we'll have cosine of 2/3 times 3 pi. That's going to be cosine of 2 pi. And we know cosine of 2 pi is 1. Okay, so now we're ready to graph this. Now they did not ask us to compare it to the original cosine function this time. We're just free to just graph this like it is. So we'll take these x values that we got, we space them out as evenly as possible on our x-axis. Okay, we have 4 intervals, so I'm going to put one here. That's going to be 3 pi. And then halfway to there would be 3 pi over 2. And then halfway from here would be 3 pi over 4. And in between these two we would need 9 pi over 4. And we're going to put in 1 and -1 on the y-axis, because that's the max and the min. So now plotting these, we've got ordered pair 0, 1. Change my color. Ordered pair 3 pi over 4, 0. When x is 3 pi over 2, y is -1. Hopefully you see how it's still that same cosine function that's just being manipulated a little bit. And then you've got 9 pi over 4, 0. And 3 pi on x, 1 on y. Alright, and then if we connect these using curves, we've got this shape, like that. So that's our graph. The interval was from 0 to 3 pi. So really the only thing different about graphing y equal cosine of 2/3 x versus y equal cosine of x is that the period is different. If it had been y equal cosine of x, the period would have been 2 pi. This one, the period was 3 pi. Well, that's example 3. Okay, next thing we're going to look at, we've got a list of guidelines for sketching graphs of sine and cosine functions. This is copied directly from the textbook. We're told that to graph y equal a times sine of bx or y equal a times cosine of bx with b greater than 0, follow these steps. First find the period, 2 pi over b. Start at 0 on the x-axis and lay off a distance of 2 pi over b. So that's what we just did. We used 2 pi over b to find our period, and then we divided that up into 4 equal parts, which is what step 2 says. Divide the interval into 4 equal parts. See the note preceding example 2. So if you want to refer in your textbook to that note, that might be helpful. And then step 3, evaluate the function for each of the 5 x values resulting from step 2. The points will be maximum points, minimum points, and x-intercepts. Step 4, plot the points found in step 3 and join them with a sinusoidal curve having amplitude absolute value of a. And then draw the graph over additional periods as needed. Okay, so these are your steps to follow for these problems. And we're going to do a couple more like this. Alright, Alright, so in example 4, we're going to graph y equals negative 2 times sine of 3x over 1 period. So the first thing we need to do is determine our period. So we're going to do y equals, we're going to do negative b over 2a. I'm sorry, not negative b. I'm so sorry, that's not right. I'm coming up with a different one. We need to do 2 pi over b. Alright. So 2 pi over b. What is b? Well, b is the coefficient on x, so that's 3. So we have period 2 pi over 3. That's our period. Alright, now once you have your period, you need to divide. Okay, so we're going to graph y equal negative 2 times sine of 3x over 1 period, and doing the formula 2 pi over b. We know b is the 3, the coefficient on the x, so that means our period is 2 pi over 3. So the rule is we have to take the interval from 0 to 2 pi over 3, divide this into 4 equal intervals. So the first thing I need half of 2 pi over 3. Half of 2/3 would be 2 over 6, or 1 over 3. So that would be pi over 3 is the midpoint. And then halfway from 0 to pi over 3, that's going to be pi over 6. Alright. And then what's halfway between pi over 3 and 2 pi over 3? Maybe if you want to convert these to common denominators, you've got pi over 6, 2 pi over 6, and that's going to be 4 pi over 6. So, okay, so we've divided our period from 0 to 2 pi over 3 into 4 equal intervals. Half of 2 pi over 3, and you may find it helpful to do, if the fractions are giving you trouble, you can convert all of these to common denominators. That might make it easier for you, because then you've got pi over 6, then you've got 2 pi over 6, which is pi over 3, 3 pi over 6 gives you pi over 2, 4 pi over 6 gives you 2 pi over 3. So these are just the simplified versions. So if you're having trouble with the fractions, just use common denominators to help you. At any rate, these are the values that we're going to put into our table for x. So we go to our table. 0, pi over 6, pi over 3, pi over 2, and 2 pi over 3. Okay? And we're going to find y equal negative 2 times sine of 3x. Alright, and let's see, to do this, let's build this. Let's start by just doing y equal sine of 3x first. And once we get that piece of it, let's just do a third column where we multiply by negative 2. So y equal negative 2 times sine of 3x in our last column. Okay, so I'm saving the coefficient for the last step. So I'm going to fill in this column for y equals sine of 3x. So I put in 0 for x. That gives me sine of 0. Sine of 0 is 0. Okay, if I put in pi over 6 for my x, I'm going to have y equals 3. I'm going to have y equals sine of 3 times pi over 6. So putting pi over 6 in here for x, I've got y equals sine times 3 times, y equals sine of 3 times pi over 6. That's going to be sine of pi over 2. And sine of pi over 2 gives me 1. I'm now put pi over 3 in for x, and I will have 3 times pi over 3. So that's going to be sine of pi, which is 0. Then put pi over 2. That's going to be sine of 3 pi over 2, which is negative 1. And then finally put in the 2 pi over 3. So that's going to give you sine of 2 pi. Sine of 2 pi is 0. Alright, and I'm sorry, I didn't draw that line correctly, but this should be 2 pi over 3 in this last row. Oops, there you go. So so when we put in 2 pi over 3 for x, we're getting 0. And there's the other one. Alright. Alright, so it looks like we've got just enough space left on our page to get our graph squeezed in. I don't know. Okay, so we got the sine of 3x filled in. Now we need to fill in negative 2 times sine 3x. So to finish it up, we just multiply these y values by negative 2. So that's going to give me 0, negative 2, 0, positive 2, and 0. Alright, and then hopefully we've got just enough space left on our page that we can actually graph this. I'm going to have to squeeze it in a little tight here. So our y values are ranging from negative 2 to positive 2. So make sure you've got that much on your graph here. And then our x values are going from 0, and our largest x value was 2 pi over 3. So it'll be out here. And then halfway, the middle point was pi over 3. And then we also have pi over 6. And 2 pi over 3. Alright. Now, we need to find the points. Order pair 0, 0. So we're going to be reading the x coordinates from our first column, and our y values are coming from our last column. So we have order pair 0, 0. Order pair pi over 6 for x and negative 2 for y here. Then we've got pi over 3 for x, 0 for y. And then pi over 2. Okay, how did I manage that? Did I mess up? Pi over 3. Oh, I see what I did. I labeled that wrong. This next to the last point down here is supposed to be pi over 2. Let me fix that. This is pi over 2. Apologize, I don't have my whiteout with me. This should be pi over 2 here. Okay, so pi over 2 for x, 2 for y, puts me here. And then 2 pi over 3 for x, 0 for y. So we're getting that same sine function that we had before, except it's got a different period, it's got a different amplitude. And also you'll notice that that negative in the front, it has affected the graph as well. Just like with any function, if you multiply it by a negative, it's going to flip it across the x-axis. So that's exactly what's happened here. Whereas it originally would have gone this way, it's been reflected across the x-axis. But this is our function. So our amplitude is 2, because that's the max is 2, min is negative 2. Our period is 2 pi over 3. And that's what our graph looks like. So that was example 4. And example 5. So this is what we just stated. Notice that when a is negative, the graph of y equal a times sine of bx is a reflection across the x-axis of the original function y equal absolute value of a times sine of bx. In example 5, we want to graph y equal 2 times cosine of pi over 2x over 1 period. Okay, so we first have to determine what our period is going to be. To get our period, we're going to do 2 pi over b. So that would be 2 pi over b, this time is the pi over 2. So that's 2 pi times 2 over pi, which is 4. So period is 4. Alright. Okay, so let's do our table. These values that we got when we divided the period into 4 intervals are going to go into our table. So we just put regular whole numbers in this time. And then over here we're going to do it. Let's do a column for cosine of pi over 2. Excuse me, cosine of pi over 2x. And then we need another column for 2 times cosine of pi over 2x. So if I put 0 in for x, this gives me cosine of 0, and I know cosine of 0 is 1. If I put in 1 for x, that gives me cosine of pi over 2, and cosine of pi over 2 is 0. If I put in 2 for x, I've got cosine of pi, and cosine of pi is negative 1. When I put in 3 for x, I get cosine of 3 pi over 2, and that one is 0. When I put in 4 for x, that gives me cosine of 2 pi, which I know is 1. And then I multiply this column by the 2, so I've got 2, 0, negative 2, 0, 2. And I can graph it. Alright, now notice this time the y values are going from negative 2 to positive 2. So that's similar to the last problem. So we'll find the point order pair 0, 2 is here. Change my pen. So I get this point. And then order pair 1, comma 0, 2, comma negative 2, 3, comma 0, and 4, comma 2. Gives me this. And we've got our regular cosine function graph. It's just been maybe rearranged a little bit. It's been stretched because we had that vertical stretch, a factor of 2 here, so that gave us the amplitude of positive 2, and the period was 4. Okay, so but otherwise that's just a regular cosine graph. It's just got a different period from the original. Okay, so that's what our graph looks like. And I'm sorry, I can't have a hard time eating your paper. There you go. Alright, so that's example 5. And then finally, example 6, determine an equation of the form y equal a, determine an equation of the form y equal a times cosine bx or y equal a times sine bx for the given graph. So there's 3 things really that you're having to look at. You need to determine, is it a sine or a cosine function? That's the first thing. Is it sine or cosine? Okay. Second, what is the amplitude? And finally, what is the period? Once you know this information, you can get your equation pretty easily. So does this look like a sine or a cosine function? Well, just looking at this, to me, it looks like a cosine function that's been reflected across the x-axis. If I go back and look, go back to your original sine and cosine functions at the beginning of this section. Okay, this is the original cosine right here. Okay, that's the original cosine function, and it looks similar to what we have in example 6, except it's been reflected across the x-axis. So based on this, I'm saying that this is going to be a cosine function. Okay, and it also looks like it's been reflected, so it looks like we're going to have a negative in front of it. So I'm going to start with y equals negative cosine x, and then I'll build from there. Okay, now what is my amplitude? My amplitude is what's the maximum? The maximum 2, minimum a negative 2. So my amplitude is 2. So that means, it looks like my equation would be y equals negative 2 times cosine of x. Alright, then we have to determine our period. So to do that, remember you're going to do 2 pi over b for the period. Now, what is b here? Well, we don't know yet. So we can look at the graph and see what the period is. How far does it take? How long does it take for it to go through a complete cycle? is 4 pi. So that means our 2 pi over b equals 4 pi. Solving this for b will give us the value we need for our equation, so our coefficient on x. So I can multiply both sides of that. I can get rid of this fraction if I multiply both sides by b. So I've got 2 pi equals b times 4 pi. And I can divide both sides by 4 pi. So 2 pi over 4 pi. And I can simplify that down to 1/2. So that means b is equal to 1/2. So with this information now, my equation will become y equals -2 times cosine of 1/2 x. And that's it. That's my equation. So really all that's going on here, this section is almost entirely building on material from section 171. You've got two new functions to practice learning how to graph, sine and cosine, and you're having to get used to graphing using multiples of pi, which involves fractions on your x-axis. But other than that, this is really an extension of 171 material, where you've got the vertical stretch, the vertical shrink, and you just have to know how to find your amplitude. Remember, amplitude always comes from the number multiplied to the front of the function. Alright, and then you have to determine the period, and you use your formula 2 pi over b. This is your b to help you find the period. And the negative here still means it's a reflection across the x-axis. Okay, so but that's it. That's it for section 6.3. So we'll be working on these more together soon. All right, thank you.